All right, today, get into chapter number 4. This will be a short chapter that we'll get through, and then after we get complete with this, we'll have a unit or a quiz on chapter 4, and then we'll have a unit test over chapter 3 and chapter 4 put together. So we have 2 more grades coming in here. If you're still looking at your grades and looking for grades, we have enough grades that we'll pick up some more. But today we start with chapter 4, and in chapter 4, we start combining the idea of probabilities that we had in the last chapter with statistics that we did in the previous chapters. Okay, when you go and you take a college stats class, okay, our book and even our books, it states it's statistics and probability. It's the idea of the combination of both these ideas of statistics along with probability. When you go to college, once again, you're going to take it. If you have to take a stats class in college, it's statistics and probability because these two things are connected together. As we talked about your car insurance at the beginning of this class, how car insurance rates are set up is they look at statistics for demographics of your age and your gender, and then they will calculate a probability of you getting into an accident. Because once again, the only time insurance companies lose money is when people start getting into accidents. So they look at your probability of you getting into an accident. You're a lot likelier to get into an accident if you live up in the Cleveland area and you're driving the Cleveland roads on a daily basis. Okay, so your insurance rates are going to be higher in a Cleveland area than they would be here in Wayne County. Okay, so you look at probabilities, you look at statistics and the data values, and they combine these together. So today what we're going to start doing is we're going to start looking at the idea of combining the idea of probability, and allows us to go with the idea of statistics. We have a random variable. When you talk about a random variable, a variable whose value can be determined by chance. A variable whose value is determined by chance. Rolling a die, pulling a card off a deck of cards. These are variables that are just done by chance. We have discrete variables, which are a finite number of outcomes that can be counted. A finite number of outcomes that can be counted. This is a discrete. When we talk about the idea of discrete, those are exact numbers. The number of people that are in this class. The number of people that eat lunch. Okay, there's a finite number of people. The number of wins for the football team this past year. There was a finite number. The number of wins of the basketball teams. Okay, finite numbers. Those are discrete variables. And then we have continuous variables. These are measured values, they're decimals. When you talk about measured values or decimals, these are continuous. And we talked about the idea of continuous when we discussed variables prior to this. I look at my thermometer on my phone right now, and the outside temperature in Dalton at this moment is 44 degrees. But is it exactly 44 degrees? That's a measured value. Is it 43.9784 or 44.21387? We don't know exactness to that. When we talked about histograms and probability and distributions with respect to histograms, we're going to throw this into the idea of probability. A discrete probability distribution consists of values. Once again, this is going to look like a histogram for us. Consists of values of random variables that can be assumed and the corresponding probabilities of these values. The probabilities are determined theoretically or by observation. So we have a discrete probability distribution consists of values of a random variable that can assume values that a random variable can assume and their corresponding probabilities. The probabilities are determined theoretically or by observation. When you talk about the values random variables can assume, you're just talking about the sample space. What is the sample space? What is the sample space, and what is the probability of each one of those things in the sample space? So we're going to take a look at a random variable here. Flipping a coin twice. Determine a probability distribution for the number of tails. So if we're flipping a coin twice, let's look at the sample space. When we look at the sample space, I flipped the coin twice. We can have a head and a head. We could have a tail and a tail. But then we can also have a tail and a head. But we have to worry about this because we have one more element to the sample space. We can have a head and a tail. If the head came up first, then the tail came up second. So you have 4 types or 4 different scenarios that could come up in our sample space. Because once again, it goes back to like the made free throw. If I make one free throw and miss one free throw, okay, I'm shooting 2 free throws. I make one, miss one. Well, I can make the first one, miss the second, or I can miss the first one and make the second one. So I have to worry about both of those scenarios there in the sample space. So if we take a look at a probability distribution, if I'm flipping a coin twice, we have the number of tails along the bottom here, because that's what I want here is I want a distribution for the number of tails. So in my flipping of the coins, I can have 0 number of tails, 1 number of tails, or 2 tails. If I look at my sample space, I have 0 tails, I have 2 tails, then 1 tail, 1 tail. Along the right-hand side is probability. So here's your sample space. That goes along the bottom here. And along the side, we have probabilities for each one of these sample spaces for a given scenario. So you're looking at sample space and the probability of that sample space. Well, if I take a look, I have 4 different scenarios over here. I can have a head, head, tail, 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 head, head, tail. of those four, what would be the probability of flipping 0 tails? What would be the probability of flipping 0 tails? Well, I can have a head, head, tail, 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 head, tail, tail. How many of the 4 have 0 tails? Well, that's the first case. It's just head and a head. So if I have a head and a head, I have 0 tails. So I have one scenario up here out of the 4 that has 0 tails. So if I have 1 out of 4, that probability of getting 0 tails is 1 out of 4. So your probability of 0 tails is 1 out of 4, which is 25%. So I'm going to put a 2, 5 there. So it's like an ordered pair here. We have a 0 number of tails. I have a 25% chance of that. If I look at my scenarios over here, how many of the 4 have 1 tail? Well, 2 of the 4 have 1 tail. We have tail, head, and then we have a head, tail. So 2 of my scenarios have 2 tails out of the 4. So 2 out of 4 would be 50% or a 0.50. So I can make an ordered pair. If I have 1 tail, I got a probability that's 0.50. And then 2 tails of my scenarios there, I have 1 of them with 2 tails. So I'm still 1 out of 4, which is 0.25 again. So it looks like ordered pairs. To complete our probability distribution, all we do is draw a vertical line down to the sample space, or the x-axis. And this would be a probability distribution. You can think of this once again as sample space. We have our sample space and our probability of sample space. We have 0 in our sample space, and the probability of that is 0.25. Rules for probability distribution. The sum of the probabilities of all the events in the sample space must equal 1. One of these scenarios must happen. If I'm flipping a coin twice, I'm either going to get 2 heads, 2 tails, or tail, head, head, tail. There's no other options. So if I add up these probabilities, they should add up to 1. 0.25 plus 0.50 plus 0.25, they add up to 1.0. The probability of each event in the sample space must be between 0 and 1. We cannot, and we can include 0 and 1. We can't have a negative possibility. Even though the coaches will say to you, you need to give 110% tonight. There's no way of exceeding your effort by an extra 10%. Your 100% is your 100%. Now, everybody's 100% might be a little bit different, which is fine, but you give your, of course, maximum effort, which is your 100%. But everybody's 100% is a little bit different. There's no way of giving more than 100%. There's no way of having a probability that's greater than 1. So if we take a look at 3 scenarios here, determine whether the distribution represents a probability distribution. Okay? Probability distribution, there's 2 rules. You must be able to add them up to equal 1, and all their probabilities must be between 0 and 1. So what we have here along the top here is we have a sample space, Okay, whatever the event is, don't know what the event is, but you can get a 1, 2, 3, or 4. That's your event. That's the sample space in the event. The probability of getting a 1 is 0.5. The probability of a 2 is 0.2. Probability of a 3 is 0.1, and the probability of a 4 is 0.3. So this is our outcome. This is our probability of each one of these outcomes. Probability of getting a 1 is a 0.5. Probability of a 2 is a 0.2. Probability of a 3 is a 0.1. Probability of 4 is a 0.3. Is this a true probability distribution? Well, if this is a true probability distribution, two things must occur. I must be able to add them up to equal 1, and I have to have my probabilities between 0 and 1. So if we take a look, probability, let's add these up. Does my probability add up to 1? I have 0.5 plus 0.2 plus 0.1 plus 0.3, which adds up to 1.1. My probabilities don't add up to 1. So this is not a probability distribution. And the reason why is the sum of my probabilities does not equal 1. If I add up all my probabilities, remember that's sigma, means add up your probabilities, does not equal 1. Not a probability distribution. My second scenario. My outcomes are, I can get either a 2, 4, 6, or 8. Who do we appreciate? I can get a 2, a 4, a 6, and 8. The probability of each one of these outcomes is listed below. Is this going to be a probability distribution? If not, why not? That's exactly correct. If I add these up, they add up to 1. I'm good with that one. But the problem we run into is our probability of an 8 is a negative 0.2. If I look at my second scenario here, my probabilities have to be between 0 and 1. My probability is a negative. So this is not a probability distribution. And the reason why is the probability of 8 is a negative. So that's our probability or reason why. So if we take a look at the last one here, our sample space is a 5, 10, 15, or 20. Those are the 4 things that could occur. I have a 0.4, 0.2, 0.1, 0.3. Okay, so let's look. Is this a probability distribution? Well, do they add up to 1? And is all my probabilities between 0 and 1? And the answer to both of those is yes. So yes, this is a probability distribution. If I would add these up, they add up to 1.0, and all my probabilities are between 0 and 1. So I'm good to go. In the first part of your homework tonight, this is what you're going to be doing. You're going to be looking at doing some probability distributions and seeing if we have a probability distribution. Like I said, we start combining the idea of probabilities with the idea of statistics, the combination of these things. We can calculate the mean of a probability distribution. We have x1, x2, x3, x4, x5. These are the outcomes, whatever the outcomes are. This is your sample space. When I put a p there, this is the probability of each one of those sample spaces. Okay, so it's the exact same thing we just did on those charts, but just I have to put it in random variables. I had to put in a formula form here. So we have outcomes and we have probability of the outcomes. We have outcomes and we have probabilities of the outcomes. We can calculate the mean of this. Our mean, once again, mu, by taking our outcome and multiplying it by the probability of that outcome. So to calculate our mean, we take our outcome and multiply it by its probability, corresponding probability, which is sigma x times probability of x. So we have the sum of the outcome times the probability of that outcome. We take the outcome and multiply it by its probability. When you talk about the expected value is just the mean. When we have an expected value, this is just the mean. We're going to do two different problems here. Taking a look at this, we have rolling a die. If we roll a die, we should have a 1/6 probability of getting each face upwards. We have a 1/6 probability of facing or getting each face put upwards. To calculate the mean, we take the outcome and multiply it by the probability of the outcome. So we have a 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 plus 4 times 1/6 plus 5 times 1/6 plus 6 times 1/6. We are just taking the outcome and multiply it by the probability of the outcome. So we have 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. So adding these up, we have 1 plus 2 plus 3, that's 6, plus 4, that's 10, plus 5, 15, plus 6, 21 over 6, which is a 3.5. Now, how we can sort of interpret this a little bit is if I would roll a die 6 times and take the average of those 6 rolls, I would expect that the average of those 6 rolls would be 3.5. Now, if we go to the front side again, let's calculate the mean of our one probability distribution. This last one down here, let's calculate the mean. To calculate our mean, we take our outcome and multiply it by its probability, and we add them up. So we have 5 times 0.4 plus 10 times 0.2 plus 15 times 0.1 plus 20 times 0.3. So we take our outcome and multiply by its probability. So we should come up to 11.5. As our mean value. If we take a look, mean, what we talked about with respect before, with a mean is a central tendency. It is a number that's in the middle of all the rest of the numbers. That is what we talked about with respect to the mean, the number that's in the middle of all these other numbers. Well, if we take a look, 11.5 would be closer to 10 than it would be to 15. And if we take a look at the weight of probabilities, to the left of 11.5, we have a 0.6, and the other two, we have a 0.4. So we have a 40% chance of getting a 15 or 20. We have a 60% chance of getting a 5 or a 10. So we have a higher chance to get a 5 or 10 than we do a 15 or 20. So my probability, my middle number here would be 12.5, would be my middle number between 10 and 15. That would be true if I had equal on both sides. But since I'm weighted a little bit more to the left, my mean's going to shift a little bit more to the left. Standard deviation, or our variance. We take our outcome squared times our probability minus our mean squared. So when we're talking about a variance, we have outcome squared times its probability minus the mean squared. So if we take a look at what we were just dealing with, this calculates the variance and standard deviation. The variance is equal to the sum of x squared times p of x, and then we subtract off our mean squared. So if we take a look, we have 5 squared times 0.4 plus 10 squared times 0.2 plus 15 squared times 0.1 plus 20 squared times 0.3. And then we subtract off, and this is typically what is forgotten and a lot of times, we subtract off our mean that we just calculated. So 25 times 0.4 plus 100 times 0.2 plus 15 squared times 0.1 plus 20 squared times 0.3. So this comes down to 172.5 minus this 11.5 squared. So we should come down to 40.25. And then our standard deviation is equal to square root of our variance. So we can take the square root of that to get 6.3 with our variance, our standard deviation. Okay, you'll be asked to do this also in your homework for today. And if you don't get all this, you can always go back to the notes. I'll post the notes on Classroom, and you can look at the notes on Classroom. Let's take a look at one last type of problem. Number of games played in the World Series from 1903 to 2009. And as I got this data out, I was surprised that it used to be a series of a best of 9 series. But what happened back in the early 1900s, in the early 1900s, there was only an American League and a National League. They didn't take 6 teams, 8 teams to the playoffs. They took a winner from the American League, they took a winner from the National League, and they had a series, and that was their World Series. They did not have all these playoffs games because to travel from one place to the other, they had to get in trains. They had to get in trains or take buses from one town to the next town. So if you had a town in New York and a town in California, they had to bus themselves from one town to the other. So they had to allow a couple days travel time just to get from one place to the other. So they just had 2 teams went to the World Series. Well, what's different about this is we have frequencies, the number of outcomes. This is your sample space. And the number of times this occurred. Number of times it occurred. But what we don't have here is we don't have a probability. Okay? So what you have to do is we have to create a probability of our sample space. Well, if I take a look, we have a total of, let's see, 20 plus 46, 36 plus. We have a total of 105 games. The probability of having 4 games, well, that goes back to our probability of favorable outcomes over total number of outcomes. So we have 4 out of the 105. I'm sorry, that would be 20 of the 105. So we have a fraction that we can change into a decimal. So we take 20 divided by 105. Try it again. 20 divided by 105. You come down to 0.19. So you had a 19% chance of having 4 games. Then we have 23 out of 105. So you have to create a probability for each one of these. To give us 0.22. This is also 23 out of 105, 0.22. Then we have a 36 out of 105. Which is 0.34. And then we have a 3 out of 105, which is 0.03. So we can make a probability distribution and you don't have to get crazy with the probability distribution. I'm going to put my probabilities, this is my probability, and here's my sample space. we have 4, 5, 6, 7, 8. And my probabilities, probability of 4 is 0.19, we have 0.22, so we have a 0.03 is my 1, then we have a 0.19, 0.22, and a 0.34. And I'm not going to space them out or signify any spacing to that. I'm just going to get my probabilities there. So I have a 0.19 with my 4, 0.22 with my 5 and my 6, 0.34 with the 7, and 0.03 with my 8. And I draw my vertical lines. And the last thing we'll look at is the mean. Our mean is our outcome times probability of outcome. So we have 4 times 0.19 plus 5 times 0.22 plus 5 times 0.6 times 0.22 plus 7 times 0.34 plus 8 times 0.03. We take outcome, multiply it by its probability. And you come down to 5.8. So if you look at the idea of a mean as an expected value, what you would expect is that you would go 5.8 games or 6 games in a World Series. That is a typical expectation based on our data that we have by the number of World Series games that have been played over the decade there. And you can do the standard deviation also by squaring each one of those values and subtracting off the mean. Okay, you have a worksheet for your homework. Solutions will be posted on Classroom also. These notes and the video will also be there. So if you missed something, I try to keep myself slow enough, slow it down. But if you had trouble keeping up, you can always go back to the notes and work with the notes. Just looking at your variance real quick, we have 4 squared times 0.19 plus 5 squared times 0.22 plus 6 squared times 0.22 plus 7 squared times 0.34 plus 8 squared times 0.03. But then don't forget to subtract off the mean squared. So if there's time, that this is actually in the notes. Let's see, we have 16 times 0.19 plus 25. It's 36 times. This comes down to 35.04 minus a 5.8 squared, which comes down to 1.4. And then the standard deviation, the square root of the 1.4. 1.2. Once again, homework is a worksheet. We'll continue to work through this. It's a fairly short chapter to get through with respect to probability distributions. Hope everybody has a good day. Adios. See you tomorrow.